right? Now let's start to take a look at how we can apply this to slightly larger things, okay? So now we're not dealing with a single central atom, but just like we did doing geometries, we can look at individual central atoms. So let's take a look at and call this carbon number 1, okay, this carbon on the left. How many areas of electrons are around that carbon, right? We have 1, 2, 3 areas around that carbon, right? So 3 areas means S, P, and P, or we call that sp2. Okay, so carbon number 1 is sp2 hybridized. Okay, and then we can look at carbon number 2 and it's exactly the same, so it's also sp2 hybridized. Now remember, sp2 has 1 unhybridized P. Okay, because remember we had 3 P's to start with. Remember we've got an S and we've got 1, 2, 3 P's. And if I take and combine 1 S and 2 P's, that means that I've got 1 left over that is unhybridized. Okay, and guess what? That unhybridized p orbital is what's responsible for that extra bond. Okay, and we'll get to that in a second with a better drawing. But let's take a look at this particular thing. So we have 3 central atoms in this molecule. I've got this carbon, and this oxygen. Okay, so let's take a look at the hybridization around each one of those things. All right, so our carbon on the left has 4 areas of electrons, so sp3. Okay, our carbon in the middle has 3 areas, so we call that sp2. Let's take a little, this guy. Now our oxygen has 4 areas, sp3. Okay, so in case you're still trying to figure out areas, let's go ahead and sort of count those, go through counting those up. I'll use a green, lighter green this time. So talking about our carbon on the left, there are 1, 2, 3, 4 areas of electrons around that carbon. That's why we get 4 areas and sp3. So S and 3 P's makes 4 things, sp3. Our central carbon has 1, 2, 3 areas of electrons around it. So S, a P, and a P, that makes 3 things, sp2, and that will have 1 unhybridized p orbital to play with. And then our oxygen, remember, lone pairs count as an area, so our oxygen has 1, 2, 3, 4 areas around it. So S and 3 P's makes 4 things, or sp3 hybridization. Okay? All right, now let's talk about how those unhybridized p orbitals come into play. So ethylene has a basic Lewis structure that looks like this. And we kind of played with this this one up there a little bit higher in the slides. All right, so we decided that each of these carbons are sp2, right? Which means that we have 1 unhybridized. That should be Z. Anyway, you know what that says. 1 unhybridized p orbital. Okay, and that is this right here. Okay, so each of these purple ones, these are all sp3, sp2 hybrids. Okay, and so when I look at the larger image of this molecule, these are the bondings of my sp2s. Okay, so each one of those bonds is an sp2 hybrid orbital doing its work. Okay, so sp2, 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 and so on and so forth. sp2, sp2. Okay, so all the sp2s are doing the direct orbital overlap. Okay, and that's right here, direct overlap. Okay, and when you have direct overlap, that means that you have what's called a sigma bond. Okay, so every time you have a direct overlap, you have a sigma bond. Okay, so let's sort of clean this up a little bit so I can talk about the next idea. Okay, so what happens is these unhybridized p orbitals, they are sticking up and down in the z-axis together, right? These are both sticking straight up and down, whoops, sticking straight up and down in the same axis, right? And so what you get is an indirect overlap okay, an indirect overlap of these p orbitals. Okay, and when you have that top and bottom, that creates a single pi bond. Okay, so let's take a look at what that sort of looks like. Okay, so over here, this plane, that's all of my sp2 bonding. Okay, that's all being done in the sp2. And then I've got these unhybridized p orbitals, and they're going to sort of at a distance share. Okay, so these are side-on interactions. All right, remember, I'm going to come back up here. So over here, my direct overlap of orbitals makes sigma bonds. Okay, in these sigma bonds, they're actually physically overlapping each other. Right, there's actual crossing of orbitals. Right. But with my unhybridized p orbitals, they're not actually touching each other. They're not actually overlapping, but they're aligned in such a way that they can share their electrons over a distance. And so what we get is this sort of above and below thing, which makes one extra bond. Okay. Now it's kind of confusing, but you got to trust me on this, that when you get that overlap above and below the plane, you get a single extra bond, and we call that a pi bond. Okay, it's the overlap of unhybridized p orbitals. Okay, that's why we want to keep track of how many unhybridized p orbitals there are. Right? So let's take a look at something more complicated yet. Okay, acetylene, if I were to draw the Lewis structure of acetylene, it's going to have a triple bond between the carbons. Okay, so what would be the hybridization of each carbon? Each carbon has two areas around it, so each carbon is simply an sp hybrid, right? So if they're sp hybrids, each one of those has two unhybridized p orbitals. Okay, so I'm looking at the diagram over here on the left, right? So you see your sigma bonds. Your sigma bonds, those are the SPs. Doing their bonding, their direct overlap. Right? So I have 3 direct overlaps. That means 3 sigma bonds. Okay? So then, to clean this up a little bit, and we'll use a slightly different color. Okay, so I've got two sets of unhybridized p orbitals. Each carbon has two unhybridized p's, right? And they are sitting right here. There's one unhybridized p, and the other one is in the, I guess, the y-axis or the x-axis. So that's sitting right there, and the other one is sitting right there. Okay, so we get direct or a sidelong overlap right here, and then we get another sidelong overlap front and back. Okay, so our drawing in the middle is showing that top and bottom. So here's your top and bottom, and then here's your front and back. Okay, so what you end up with is sort of a sandwich, which makes two. We have two pi bonds. Okay. So if I have three direct overlaps, I have three sigma bonds. If I have two indirect interactions, I have two pi bonds. Okay, and there's actually, and so we're doing all this direct overlap, indirect interaction terminology, but it's actually a lot simpler than that to determine how many sigma or pi bonds there are. Okay, so counting sigma pi bonds, and I've got this wonderful sort of hideous molecule to look at. So easiest thing, so all bonds count for one sigma bond each. Okay, so the first thing you want to do is just count up all of the places where there's a bond happening. Okay, and then so any extra lines count for 1 pi each. Okay, so let's take a look at our big ugly molecule here. Now the first thing I want to do is just count every bond. Count all bonds. Okay, I'm going to go through and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so each place that something is connected to another thing counts for a sigma. So I have 17 sigma bonds in this molecule, provided I didn't miss any. Okay, so now I'm gonna back up here. Sigma bonds. Let's see if I can delicately erase things to clean things up, especially in our double bond places. Double and triple bonds. Okay, so any place that you have an extra line counts for a pi bond. So we have 1, whoops, that's the eraser. Make that green. Right, so we have 1, 2, 3, 4, 5, 6 extra bonds. So that means that I have 6 pi bonds. Okay. So now let's take this another step further, and let's see if I can clean this up again. At least get rid of some of these extra lines. Let's take a look at hybridizations. Right? So just about all of the carbons in this ring, right? Let's look at the top carbon in the ring. Let's look at this guy right here. right? So how many areas of electrons are around that carbon? And the answer is 3. So that carbon is sp2 hybridized, right? 3 areas, right? So the carbon just to the right of it, this carbon, 1, 2, 3, also sp2. This one is sp2. All of these carbons are going to be sp2. Okay, because they each have 3 areas of electrons around them. All right, let's come to the bottom of the ring and that branch that comes off of it, and let's look at this carbon. What is its hybridization? And it's got 2 areas of electrons around it, so it's sp. Okay, same thing with the carbon below it. This carbon is also sp because it has 2 areas of electrons around it. Okay, so moving to the right-hand branch off of the ring, the first carbon that we run into is this one, and it has 3 areas, so it's also sp2. Okay, the oxygen has 4 areas of electrons around it, sp3. Okay, so we can determine all kinds of things about molecular shape now, and hybridization, and sigma and pi bonds, all kinds of wonderful things. We have lots of information now.